who is going to talk about quasi-modularity of Hodge cycles.
Okay, thank you very much for the invitation. It's an absolute pleasure to be here. So what I want to talk about today is how to count instances of these Hodge cycles that the rest of the conference is about. So just to set things up, I'll focus on the case of surfaces, so Noether-Lefschetz loci. Just a fixed notation, let's take V over S to be a Z polarized variation of Hodge structure of weight 2. And so just like we had in Greg's talk, you can interpret this as a map from S to D mod gamma, the period domain. And if you'd like, so let's say the type of the Hodge structure is P comma N comma P. You can pass to a further quotient by the maximal compact subgroup. So instead of D mod gamma, you're getting O2P comma N mod O2P On, which you can think of as the Grassmannian of positive definite linear spaces inside R to the 2P plus N. So mod gamma. And here gamma is going to be the automorphism group of some of the lattice, so the integral lattice structure on your integral polarized variation of Hodge structure. Okay, so the first kind of theorem where you get some modular forms is due to Kudla-Millson from 1990. And what it says is if you consider these totally geodesic subvarieties of this bottom space, so CD is defined as the locus of W in this positive definite Grassmannian, such that W is orthogonal to some integer vector V in the lattice, where V has self-intersection minus 2D. And then let me quotient by the arithmetic group. Okay, so this is a codimension. So this CD is inside of this Grassmannian plus of codimension 2P. Okay, so that's just the definition, and the theorem is that if I assemble all of the classes of these cycles into a generating function, so the sum over all D of CD Q to the D. So technically, I guess I'm taking the Poincare dual here, so I want to view them as cohomology classes. These are non-compact cycles, so I'm kind of taking the Poincare dual of the Borel-Moore class of the non-compact cycle. And the theorem is that this is a modular form. So it's a modular form with values in the cohomology of this locally symmetric space. So the modular form has weight equal to half of the rank of the lattice. And it's valued in H2P of this locally symmetric space. Okay, are any questions about this statement? Yeah. Yeah, so I'm taking a union over all V with this length, and there's up to the action of gamma. There's only finitely many such V. So this is actually a finite cycle. Yeah, good question. Yeah. I'm quotienting by. I'm quotienting by gamma after I take out W. Oh, yeah, thanks. Yeah, sorry. Yeah, completely classical. It's not level, so the level will depend on the discriminant of of the lattice. So, so if the lattice is unimodular, it'll be level 1. If the lattice has some higher discriminant, then it will be correspondingly higher level. You can also soup this up and keep track of the class. Okay, let me just state it like this. I think it's easier. And so what does it mean to be a modular form valued in this cohomology? Another way of saying that is that if you take any element in the dual, then if I pair this dual element with every coefficient of the power series, then I just get an honest modular form where the coefficients are numbers. So 2p plus n over 2. Okay, and that's actually how the theorem is proved, is by testing against homology classes. So the dual of G R mod gamma. Okay, and so why would you care about this? Well, there's lots of applications in enumerative geometry. So if the base of your variation S was compact and its dimension was the correct, so dimension over C of S was P, then take your mu to be the period image of S. And this gives you counts then of the Noether-Lefschetz loci on S. Okay, but as we all know, it's kind of rare to find a variation of Hodge structure over a compact base. So if S is non-compact, then we need a new theorem. We need to first of all compactify S and get some map to a compactified D mod gamma, and we need to intersect with the closures of these CDs in this compactified D mod gamma. Okay. So this is an application, and the advantages of this modular form statement. In my mind, there are two main advantages. The first one is that the space of modular forms of a fixed weight and level is finite dimensional. Right, so what that means is if I have one of these applications in mind, I have an S, and I intersect it with all these special cycles. As long as I know the first few coefficients of the power series, then I know all of the coefficients. So that finite dimensionality is useful. And the second thing is that we have bounds for the growth rate of the coefficients. So we have polynomial growth rate of the Fourier coefficients of a modular form. Okay, so the next thing is that there's a refinement of this first theorem which deals with higher codimension of the Lefschetz loci. So this notation will become clear in a minute. But I'm calling this theorem 1 superscript r. And so if instead we define C, D bold-faced D, where D is now a matrix, then we can define this to be a set of all W in this positive definite Grassmannian, such that W is orthogonal to a list of vectors V1 through VR with intersection matrix given by this bold-faced D. So it's -2, just as before. And again, quotient by gamma. So this is now codimension 2PR cycle. And in the same paper, Kudla and Millson also proved that if you arrange these into a power series, so phi parentheses R of Q, which is just going to be the sum now over all positive semi-definite matrices. So bold-faced D is a positive semi-definite matrix now of CD Q to the D, that this is a Siegel modular form now. So the Siegel modular form of genus R in the same weight as before, so half the rank of the lattice, and tensored with H2PR now of GR mod gamma. Okay. Exactly, yeah. So I'm going to focus, now I'm going to focus on the case where P equals 1. Sorry, where? Whatever. There's infinitely many multi-sets of vectors that have a given matrix, but up to gamma, there's only finitely many. Okay, so yeah, as you said, when P equals 1, you're in the Shimura variety case, also known as K3 type case. And in that case, we can compactify. So there exist these nice compactifications of D mod gamma by Mumford and his collaborators. So these are called the toroidal compactifications, and they show up as blow-ups of the Satake-Bailey-Borel compactification. So let me first talk about the Satake-Bailey-Borel. So this is, if I add the rational boundary components to D, so D union, so there's two types of rational boundary components. The first type is over isotropic two-dimensional planes inside the Q points of the lattice. And these give you upper half planes. And then there's a second type which is over rational lines, isotropic inside gamma Q. And these just give you points. So quotient by gamma. And the toroidal compactification is a blow-up of this guy that I'll denote by D mod gamma sigma. Mm-hmm. Yeah, sorry. The D here is a matrix. D here is R by R positive semi-definite matrix. So if you call this multi-set of vectors bold-faced V, then I'm just saying that bold-faced V dot with bold-faced V is -2 bold-faced D. just kind of with the.
What do you mean by giving positive in the sum.
Yeah, this greater than or equal to just means positive semi-definite, yeah. Yeah, I mean, somehow the way you should think of this is these are vectors which are algebraic classes in your surface, and we're just looking at Hodge structures which contain those as algebraic classes. Okay, so the way these compactifications go is first you can construct the Bailey-Borel compactification, which is a singular projective variety. And then you blow it up to get a smooth projective variety where there's a divisorial boundary, simple normal crossings, and there's a divisor over each of these strata. So there's a delta j over each of these j, and a delta I over each of these boundary strata, of these punctual boundary strata. And borrowing some notation from Kulikov for degenerations of K3 surfaces, I'll call the boundary components over these one-dimensional Bailey-Borel boundary as type 2, and the boundary divisors over the punctual Bailey-Borel boundary as type 3. And the interior of this is type 1. So that will kind of explain the notation of the theorems. Okay, so what does the geometry look like for these boundary divisors? So in type 2, if you're given an isotropic J inside lambda q, if you consider J perp mod J, this will be a negative definite integer lattice. And I'm going to tensor it over Z with the universal elliptic curve over the modular curve. And then modulo a finite group G, this is what the type 2 boundary components look like. You can count, if you want to check, you can count the dimension and make sure that this is one dimension lower than the dimension of D mod gamma. So it's a divisor. And the type 3 boundary components are all toric varieties. So delta I is a toric variety. And these type 3 components actually depend on a combinatorial choice. So this sigma notation here, there's hidden in there the choice of a fan. So in order to construct one of these toroidal compactifications, one needs to make a choice of inside I perp mod I, which is a hyperbolic lattice. We have the positive cone. So there's the cone of positive vectors inside this hyperbolic space. And we need to choose, so sigma is a rational polyhedral fan inside the positive cone of this hyperbolic space. Containing all the rational isotropic rays on the boundary of the cone as well. So just to draw a picture of that, something like this. And so it's an infinite type fan, but it has a finite fundamental domain under the action of gamma. So it has with finite fundamental domain under the action of, the stabilizer of this I inside gamma. Stabilizer of I inside gamma. Okay, and so really, gamma, delta I is a union of toric varieties, one for each ray that lies in a fundamental domain for this action. So if we just choose a fundamental domain, something like this, then for each vertex in the fundamental domain, you get a toric variety. And the toric variety is constructed out of just taking the fan that you get by taking a cross-section of the cone and just looking at the star around that particular ray. So the annoying thing is that there is some kind of choice involved in constructing these blowups, whereas the Satake-Bailey-Borel compactification is canonical. But all these toroidal compactifications agree if you're only interested in the type 2 partial compactification. The choice comes into play when you pass to type 3. Are there any questions about that? Okay, so theorem 2, where this 2 corresponds to type 2 boundary, is that if we take the closures of our special cycles in the partial compactification where we've only added the delta j's, so this is the sum, again, overall d greater than or equal to 0 of the class of CD bar. This is Zariski closure in the partial compactification. And the statement is that it looks the same as before, only we have to add a q mod instead of a mod. So 2 plus n over 2, tensor H2 of d mod gamma partial compactification. All right. So what does this mean? So q mod here means quasi-modular form. And a quasi-modular form is just a polynomial in the series E2 of Q over the graded ring of modular forms. Okay, so it's just a slight enlargement of the spaces that Kudla-Millson have. And it still has the nice properties that in any given weight, this space is finite dimensional. And it also has a nice polynomial growth rate of the Fourier coefficients. So the same kind of features hold. We just have to slightly enlarge our possible power series. And then the second thing is sort of measuring how this quasi-modularity is encoding the fact that we added some boundary divisors. So if I take the partial derivative with respect to E2, of this power series times minus 12, then I just get something that's modular and it's very well controlled. So it's just the sum overall isotropic 2 planes J mod the action of gamma of the theta function for this negative definite lattice J perp mod J, tensored with the boundary divisor that corresponds to that J. So the next theorem is if we go to the full compactification, and I define same as before, the phi 3 of Q now to be the sum over all D of the class of the Noether-Lefschetz cycle, Zariski closure now in the compact toroidal compactification. This depends on the choice of the fan sigma now. And the statement now is that instead of quasi-modular form, there's an even broader class, which is called a mixed mock modular form. Again, of weight 2 plus n over 2 in H2 of the full toroidal compactification. And there's an analog of the second statement, which involves the Zagier shadow operator. So this is kind of a generalization. It's generalization of the partial derivative with respect to E2 of a mock modular form. And so we get something very similar. So first, we need to sum over all the rational lines up to gamma. And then once we've chosen a rational line, we need to sum over each of the rays in a fundamental domain for the action of gamma on that positive cone of the theta function for this C perp of Q times the theta function of weight 1/2 associated to C squared, tensor delta I, comma C. So I won't write what a mixed mock modular form is, but I'll just say it in words. It's just a polynomial, again, over the ring of modular forms with coefficients which are weak harmonic mass forms of this weight. So, okay. So if that's all kind of very abstract, I want to kind of make it more concrete by giving an example, which ties in nicely with Adrian's talk earlier today. So I think the simplest example of these period spaces is elliptic K3 surfaces. So let's consider just H polarized K3 surfaces. So H here, it means the lattice with Gram matrix 0, 1, 1, 0, which is, if you change basis, you can write it as -2, 1, 1, 0. So a K3 surface that has this inside of its Picard group is automatically elliptic. So i.e. elliptically fibered K3 surfaces. So the moduli space, I'll call the moduli space of such things M sub elliptic K3. And by the polarized, lattice polarized K3 Torelli theorem, this is actually isomorphic to a D mod gamma, where this is now 18-dimensional. Because H perp inside of the cohomology of a K3 is some lattice lambda of signature 2, 18. Okay, so we're just doing this story in this particular case of this lattice, and because our H is unimodular, that tells us that the lambda here lattice is also unimodular, and that will make all of our modular forms of full level. So it's kind of easy to know what the generators are. Okay. All right, so in this context, what are the CDs? So CD inside of D mod gamma. This just corresponds to the set of elliptic K3 surfaces, such that in addition to the 0 section, there exists a second section of the elliptic fibration, such that it crosses the 0 section D plus 2 times. Okay, so you can say it has a height D plus 2. And there's a slight caveat. So this is true for D not equal to a square. When D is a square, there's another locus too, but let me just not worry about that for now. Okay. All right, so I can now use this theorem to answer a certain counting problem, so Gromov-Witten theory question. So if I consider now a Calabi-Yau threefold, which is elliptically fibered over a ruled surface. So the picture here is I have a ruled surface, so I have a surface which has generically a P1 fibered, but maybe with some broken fibers over some base curve. And then I consider a threefold, which is elliptically fibered over this. So this second arrow is an elliptic fibration. And I'd like to count curves on this thing. So let's call this the Calabi-Yau threefold X. So the theorem then is that if I look at Gromov-Witten invariance, so counting curves on X in class, the class of the ruling plus n times the class of the elliptic curve fiber. So there will be elliptic curve fibers here, I'll call F times q to the n. This is equal to some quasi-modular form phi of q times q over delta of q, where delta of q is the modular discriminant form. Okay, so this is a theorem that's essentially a corollary of theorem 2 over here. So the proof. So just to sort of see how this goes. So for each point in the base curve, I have a line of the ruling L, and if I take the preimage of that line of the ruling, I get a K3 surface that's elliptically fibered. So this is an elliptic K3 surface. Okay. So that gives me a map from this base curve C into the moduli space of elliptic K3 surfaces, which is isomorphic to D mod gamma. Right, but as we said, it's possible that some of these rulings break. So there are certain points in the base curve where you have a broken fiber there, and that corresponds to the K3 surface becoming singular. So it breaking into a union of two rational elliptic surfaces. So the K3 surface has 24 singular fibers, and the rational elliptic surface has only 12. So you're kind of breaking this K3 surface in half. Yeah. Yeah, that's right, thanks. So phi of q is a quasi-modular form of weight 10. I'll say what it is in a moment. So anyway, so if we're removing these finitely many bad points where the variation of Hodge structure becomes singular, then you would have a map to this D mod gamma. But if you want to have a map from the full curve, including these bad points, you need to compactify to D mod gamma toroidal. Okay, and these degenerations of K3 surfaces are type 2. So this is just going to crash into the delta J part of the boundary. And in fact, if we draw a picture of the toroidal compactification, there are two components of type 2. And they correspond to the possible J perp mod J lattices, of which there are only two. There's E8 plus E8 and D16 plus the two unimodular negative definite lattices of rank 16. Okay, so the point is, so the period image of this curve C is crashing into the E8 plus E8 part in this example some finite number of times. And so if we take the period image of this C as our class, this is a curve class, a class in H lower 2 of this compactified period space. and I intersect with phi 2 of q, the divisor-valued quasi-modular form, then from the theorem I know that I get some weight 10 quasi-modular form, which is what I wrote over there, so phi of q. And the second part of the theorem that I just erased tells us a little bit more. It tells us what happens when you take the partial derivative with respect to E2. So this phi of q is some number a times E4, E6, plus some number b times E4 squared E2. Exactly, yeah, that's right. Yeah, so we don't have like E2 to the 5, for example. That can't happen. And right, so the second part of the theorem would just tell us then that minus 12 times the number b here is the number of broken K3 surfaces in the family. So it has to, so that's equal to the number of, the number of broken rulings, if you want. And by comparing the constant terms, a plus b has to be the degree of the dual Hodge bundle. So I apologize, I didn't actually say this before, but let me say it now. You need a separate definition for the constant term of all these power series. So C0, since 0 is not a positive integer, it is also not a positive definite matrix, you need a separate definition. So C0 doesn't actually make sense as a cycle, only as a class, and it's just defined to be the Euler class, top turn class of the Hodge bundle, dualized. So Hodge bundle on d mod gamma. So this is in all the theorems. Okay. So how much time do I have? About like 15 minutes? Oh yeah, I should also mention that the presence of this q over delta q term in the theorem that I just erased this is just the Yau-Zaslow formula. So this just accounts for counting curves which have components in the fibers of your K3 surfaces. So somehow it doesn't really show up from Hodge theory. It's just kind of a figment of the Gromov-Witten problem that we're studying. So this is kind of a parenthetical. The important kind of enumerative information from a Hodge theory perspective is just this phi of q part. Okay. So first of all, if we take p bigger than 1, then the d mod gammas are no longer Shimura varieties. So we have d mod gamma. And we still have access to these Kato-Usui compactifications. So we haven't finished this yet, but I expect that there's a partial compactification, a partial Kato-Usui compactification where you just add type 2 degenerations. And we expect a similar quasi-modular statement to hold there. So we expect quasi-modular series. There. And then there's another kind of very attractive potential application of this beyond the Shimura case, which is that if you're interested in abelian varieties, so weight 1 Hodge structures, you can actually relate those to this story. So if I take A1 times AG, there's a tensor product map. So if I tensor together the two weight 1 Hodge structures, I get a weight 2 Hodge structure. And so it goes to one of these spaces considered by Kudla-Millson, which is split type, so signature 2G comma 2G. So as long as G is bigger than 1, we're definitely outside the Shimura world there. And it's a fact that if I take the pre-image of the special cycle CD under this tensor product map, I get the set of pairs E, comma, elliptic curve E, abelian variety X, such that X is d-isogenous to E times some G minus 1 dimensional abelian variety Y. So it's sort of the d-isogeny locus. So in particular, so then if I project down to the second factor, so if I take pro2 of tensor inverse of CD, I get this locus SD inside of AG. So this is the d-isogeny split abelian varieties. Okay, so it would be very tempting to then conclude that if I make a power series out of these isogeny split loci, the result would then be a modular form, just by starting with the Kudla-Millson modular form, taking pull back and then push forward. But there's a problem with this. There's a couple problems. The first problem is that the push forward map here is not proper, because A1 is a non-proper thing. And the other problem is that already when you take the pullback of the Kudla-Millson series through this, you just get the 0. Somehow there's not enough compactness in here for that class to be non-zero. So the upper star of the class of CD is actually 0 in H2G of A1 times AG. So the conjecture then is that if I first just take the set theoretic preimage under tensor product of the Deith Noether-Lefschetz cycle, and then I take its Zariski closure in a toroidal compactification, again, sum over d greater than or equal to 0, with the same convention of defining C0, that this is going to be quasi-modular form of weight 2G tensor H2G of A1 star cross AG toroidal. Okay. And this conjecture would imply another conjecture by Carl Leon, which is taking place in mg bar. So his conjecture says that in mg bar, if I take the sum of the locus of d-elliptic curves, so curves which admit a degree d cover of an elliptic curve, times q to the d, that this is in quasi-mod 2g tensor H2g of mg bar. And Carl Leon's conjecture is known for genus 2 and 3. And I can also check this conjecture in genus 2 and 3. M2 is very close to A2 and M3 is very close to A3, but the proofs are very different. So the proof here sort of uses these kind of automorphic Hodge theory considerations, and his proof uses double ramification cycles and kind of curved geometry. So that's a good thing. MG bar is just Deligne-Mumford, yeah. Is the Deligne-Mumford compactification, yeah. No, but there's the period map extend. If you take either the perfect cone or the Voronoi compactification, you can extend the period map for MGW. Yeah. So like this would just be the pullback of this conjecture, yeah, through that period map. Sorry, push forward also. Yeah. So you'd have, yeah, push forward to AG and then pull back to MG. Okay. So another question I think is very interesting is whether any of these statements hold at the level of Chow. So can we lift any of these theorems to CH star? So as we know, all the Noether-Lefschetz loci are algebraic cycles. So clearly, each coefficient in these power series has a class in Chow. But saying that the series is actually modular, quasi-modular, with values in Chow is a much stronger statement. And so kind of for trivial reasons, so theorems 2 and 3 do lift to Chow, but in that case, it's just Chow 1, because Chow 1 just happens to be equal to H2 over Q in those situations. So it kind of trivially lifts. Let me write a theorem in progress. So this, we call it theorem 2R, is that if we take the closures of these sort of bold-faced Ds, so higher codimension, Q to the D, in the type 2 compactification, that this is a Siegel quasi-modular form. Valued in H2PR of D mod gamma 2. But the interesting thing there is that the weight becomes mixed. So instead of being 1 plus n over 2, sorry, it's 2R, sorry. It's 1 plus n over 2 up to n over 2 plus R minus 1. So there's a different weight that occurs in the boundary compared to the interior when you go to these higher rank Siegel modular forms. And this, so the interior statement does lift to Chow. Chow R essentially by Wei-Zhang's thesis. So it's an interesting question to see if this result in cohomology would then lift to Chow R, again, in the Shimura variety case. And then you can also formulate this Chow question in these non-Shimura cases, but you have to be a little bit careful. You should formulate it in the Chow of this algebraic stack as opposed to this non-algebraic space. And then if you wanted to formulate this in Chow, you would need to basically formulate it on any quasi-projective variety which is mapping into this, et cetera. So maybe I'll stop there. Thanks very much.